And we're back with more stats. Today, talking about the Z table. Let's get right into it because I know we are excited. So, in the previous lesson, we learned about the empirical rule, or we're reminded of the empirical rule that allowed us to find probabilities for areas under a normal distribution of data. Now, today we're going to learn about the Z table, which again allows us to find areas under the normal distribution that don't follow and denies integer values in terms of standard deviations away from the mean. The version of the table I use is the cumulative Z table. It's posted on the course website. It's found in the textbook, and I will begin now. So, determining probabilities for any normal distribution, it's important to recognize that any normal distribution of data can be standardized. It doesn't matter if we're talking about height or volume or speed or grades. Whatever the unit is, we can standardize it, and standardization means that we're going to make it so the mean is 0 and the standard deviation is 1. For given x values, we calculate z-scores. This is the method of standardization. And then we're going to take the z-score and go to the table and find associated probabilities. Here's the formula. It's very simple. The numerator is x, the value, whatever number it is. That could be, let's say, 5.73 feet, okay, or 5.13 minutes, minus the population mean, okay, the center of that distribution, over the population standard deviation. And this is going to tell us how many standard deviations x is from the mean. All right, the numerator is the absolute deviation, and when you divide it by the standard deviation, you have the standardized deviation. So x just says, hey, I've got an x z. I'm sorry, z just says this. So listen, I got an x value. It's a certain distance from the mean, and z tells you how many standard deviations it is from the mean. Puts it in like terms. Here we have a distribution with a mean of 50 and a standard deviation of 15, as you can see with my labeled x graph. Z, of course, is going to be centered at 0. You can see how this formula works if it weren't obvious to begin with. 20 is 2 standard deviations below the mean, and 80 is 2 standard deviations above the mean, and so on and so forth. And so you keep filling in this graph, and you have the z, standardized z value. Again, the table we use is the cumulative z-score, z-table, I'm sorry. And it works like this. It gives the probability that a value lies to the left of the z-value of interest. So once you plug in a value for x, you will get a z-score, and the table is going to give you the area to the left of that z. So for instance, if you look up 2, it's going to give you the area to the left of 2, which we know should be close to 0.16. The table is going to give us a little more precision than the empirical rule. So z values to 2 decimal places are contained in the table. The first column contains the z values to the first decimal place, and the headings for columns from 2 to 11 give us the second decimal place value for z. So here is a zoomed in picture of the z table. On one side, this is the positive side. Okay, there's of course the other left side of the table is the negative side. So z scores from 0 to I think 3.9 are listed here, and you'll see that the first decimal place is here on that first column, and then these other headings of the remaining columns are the z-scores to the second decimal place. And you'll see that each of the values, these are probabilities in the interior of the table, okay, which means outside of these column headings in the first column are probabilities, and they're probabilities that you're getting less than the z-value you look up. So the probability of getting less than the z-value of 0 is 0.5, because everything to the left of the mean of 0 is 0.5, so that should make sense. So let's get some practice using the table. So if we want to use the table to find the probability that z is to the left of 1.28, that is this region shaded here, 1.28. This is the z-axis, you see. I don't have the x-axis. Often I'll have both, or in this case I only need one. Z, of course, I'm sorry, 0 is the center of that graph. But how I can use the table is I need to look up 1.28. Here I find 1.2 is the first in the first decimal place, 0.08 the second decimal place, and it's cut off a little bit, but that's 0.8997, and that's going to be the probability that z is less than 1.28, and so that's this area here in blue. Another question here, determine the probability that z is less than 0.67. Well, positive z-score, 0.6 the first decimal place, 0.07 the second decimal place, and that's going to be 0.7486. All right, we'll determine the probability that z is less than 0.678. We see that there's 3 decimal places here. We have to do some rounding. Since it's 0.675, we'll do our traditional rounding to round this to 0.68. Okay, 0.68, and then we'll use the z table to look up negative 0.68. Okay, and if we do that, you're going to find that the probability of being less than 0.68 is 0.2483. All right, sorry, I encourage you to go to the z table to look that up. In fact, let me pause this recording and I'll open up the z table to take a look. So we're here looking at the z table now, and if you recall, the last problem asked for the probability that z is less than 0.68. We got an answer of 0.2483. Let's verify that. You notice that these kind of start from 0 in the interior and then move out, so you got to be careful of that. The second decimal place is going to be 0.08 here, and so that's going to leave us with this value right here, 0.2483. And that's how the table works. Once you realize how the table works and keep that committed to memory, you should have no problem going back and forth at the z table. So in summary, how can we determine probabilities for a normally distributed random variable? Well, if the problem allows, if the area under the curve of interest falls within nice integer values in terms of standard deviations, we can use the empirical rule. Okay, if it's 1, 2, 3, or any combination of standard deviations above or below the mean. But for anything beyond that, we'd like to use the z-table. Now, with the z-table, you could confirm the empirical rule, again, to 2 decimal places, so it's a little bit more precise than the approximations of 68, 95, and 100%. But you certainly, and I encourage you to take on that activity to use the z-table to try to verify the empirical rule. Again, that around 68% of the data, for instance, is within 1 standard deviation above and below the mean. To reiterate, every normal distribution can be transformed into a standard normal distribution. So we can use that z-table for any data we have. Looking at another problem, let's go in a different direction. Previously, we were looking at areas below a certain z. Let's look at how to use the table to find an area above a z-score of 1.35. The empirical rule isn't going to give us enough information here. You know, we can kind of guess it's going to be somewhere less than 0.16, greater than 0.05, but we'll have to look at what that is. And so if we look up 1.35 on the table, we get 0.9115. That's the area that we don't need. We need the complement of that. And so we're going to get 0.0885 as our answer. So the probability of being greater than a z-score of 1.35 is 0.0885, or another way to say it is an 8.9% chance of being above 1.35. We have another example here where z is an interval. So it's not from one z-score indefinitely towards a tail. It's an interval, in this case, between the mean and 1.5. And so if we look up a couple z-scores here, look up 1.5, we get 0.9332. Well, that's the area from the below 1.5 to negative infinity, but we have to subtract 0.5 from that, right? Which is the area less to the left or less than the mean. And so we're left with 0.4332, and that would be our answer. So that probability in blue is 0.4332. Kind of one of the final examples we could use is an OR probability. So we're looking at two areas here. The probability that z is less than negative 1.15 or greater than 1.5, and I have my fancy bubbles in here shading these regions. But we're going to use the z-table in the same way. You know, I could look up the negative 1.15 and I get 0.1251, and that is the answer to the left shaded bubbled region. And then I look up 1.5 and it's going to give me 0.9332, but that's not what we want. We want the complement of that, so we want 0.0668. So 0.0668 plus 0.1251 is giving us 0.1919, and that is the answer to that problem. So now we'll do some examples using the z-table. Okay, in this example, the variable x is distributed normally with a mean of 40 and a standard deviation of 20. And it says to determine the following probability, capital P there, that x is between 30 and 65. You'll see that on this PowerPoint slide, I have this kind of graphed drawing application. It's actually, I'm using my iPad, but that's why you see that different kind of color or scheme up there and different icons. But anyhow, we know that the distribution is normal. Distribution of x is normal, and it has a mean of 40. I'm doing this with my finger. I'm locking my stylus at the moment. Hopefully it's okay. And a standard deviation of 20. I'll draw in a couple standard deviations in both directions. And we're looking for the area. Let's do this in red, between 30 and 65. So roughly, this area in red is what we're after. And in order to do so, we have to standardize this distribution. We will go ahead and include the z-axis under the x. And we need to find two z-scores here. Now the first one we'll find is the one that corresponds to an x value of 65. Let's try that again. No better. We get the point. 65 minus 40 over 20. And we're looking at 1.25 is my z. And I go to the z-table. I encourage you to do so. And if I go to the z-table, I'll find that the area to the left of 1.25, right, all of this is 0.8944. Okay, we don't need that entire area because we have to subtract the area to the left of the first red line there. And to find that area, we'll calculate our second z-score, which is going to be 30 minus 40, so negative 10 in the numerator, 20 in the denominator. That's negative 1/2, so negative 0.5. If you look up negative 0.5 in the z-table, you're going to get an area of 0.3085. And very simply, the answer to this problem is going to be the 0.8944 minus the 0.3085, which is 0.5859. And so 0.5859 is the answer to the problem. That's the probability of x being between 30 and 65. So let's look at this next problem. We have An example where adults on average, the data set says that watch 4.28 hours of TV per day. This is data set's quite dated, 1995, and a standard deviation of 1.3 hours. And the data are assumed, or we're told that the data are normal following the bell shape. There are two questions. We'll address the first one first. What's the probability that a randomly selected adult watches less than 2 hours of television per day? So the probability that X is less than 2. And then we'll follow that up by looking at how much TV would an adult have to watch to be at the 99th percentile. To be watching enough TV that 99% of the population is going to be watching less TV. So we'll look at this one first. I'm going to prepare this application here. Let's move this a little bit. Okay, that should work. Okay, so we'll begin with drawing the distribution as a normal bell shape. X is TV time, right? We know that the distribution is normal with a mean of 4.28 hours. And if you recall, the standard deviation is 1.3. So one standard deviation below the mean, for instance, would be 2.98 hours. Two standard deviations below the mean would be 1.68 hours. A little awkward here with this amount of room. But in red, we're looking at the area of 2 as kind of a cutoff. And we want to know at first the probability that someone watches less than 2 hours per day. So this area in red. And it's just a simple application of the Z, right? We need to find what that Z is, and then Z would be, in this case, 2 minus 4.28 over 1.3. And that's going to be negative 1.75. You go to the Z table, you look up a Z-score of negative 1.75, and you'll get an area to the left of 0.0401. And that's exactly the answer to this. About 4% of people are watching less than 2 hours of TV per day. And this last example is the question again, how much TV would the adult have to watch to be at the 99th percentile? I'm again going to draw the Z distribution. I'm sorry, the distribution of data, which would be X TV time and, of course, a Z. And this one requires us to move in a different direction. We know that the mean is 4.28 hours. What we're looking for right now, and I'm going to put this in blue, circle it, is the number of hours that a person watches such that 99% of the population is watching less TV than them. And so we need a Z for which, if we looked it up on the table, the area to the left would be 0.99, the closest we can get. And that Z, if you look on the table, is going to be 2.33. So instead of looking at finding a Z and then finding the probability associated with it, right here we're finding a probability, which is 0.99, and tracking back the Z that's associated with that. And then once we do that, we utilize the same Z formula. That denominator is a standard deviation. And we know that we have 2.33. We need X. We have our mean of 4.28. And we have our standard deviation. And if you back it all out, X equals 7.309. All right, and that's the answer to the problem, that someone at the 99th percentile is watching About 7 1/3 hours of TV a day, which is, even by today's standards, quite a bit. And that, again, the data set was from 1995.